Welcome back to our series on multivariable calculus. In this episode, we're going to talk about multiple integrals. In particular, we're going to feature double integrals, although the techniques we look at today can be extended to integrals in more dimensions than 2. What I do today won't really constitute a proof that these multiple integrals are representing what we claim they're representing. Plenty of proofs are available both online and in your textbook. So instead, what I'd like to do is devote our time today to making sense of these double integrals. And to do that, let's talk about the definition of an integral that you learned in integral calculus. And that, of course, is based on a Riemann sum. In a Riemann sum, we would take a summation I equals 1 to some variable n of f of xi, where each xi was then determined and plugged into the function, and that would give us the height of the function at that point. Then we'd multiply by delta x a little width, and in essence we're constructing a rectangle of width delta x and height f of xi. We're going to do this a number of times, and if we break the function up into a series of rectangles, then the area of that sum of rectangles will approximate the area under the curve, which of course is what an integral is. There are many techniques for determining f of xi. You can use the trapezoidal rule, or the left side, or the right side, or the average of the function over delta x. And we're not going to really worry too much about how that height is determined because we're not actually going to perform this sum. We want to immediately turn it into an integral. And of course, we do that by taking the limit as n goes to infinity. So we're going to break up into an infinite number of pieces, and we're going to allow those infinite rectangles to actually sum to the area under the curve. And of course, what does this produce? This produces our familiar integral, the integral from a to b of f of x dx, where delta x is replaced by dx, an infinitesimal piece of the width of the function. A and b then represent the limits, and in order to determine the limits, it's where we're going to start integrating. So in essence, it would be where the first xi value is, x of 1. And then if we multiply delta x by n, the number of n's, that'll tell us how far down we're moving, and the opposite end would be b. So the interval from a to b simply represents how wide an integral we're after. Okay, so that's a piece of calculus that you're already familiar with, taking Riemann sums and turning them into integrals. Well, let's take a look at what happens when our function is two-dimensional. If instead of f of x, we want to do this to f of xy, well, we know that means we've got some sort of z function that hovers over the xy plane. And what we want to do now is perform two nested Riemann sums. The first one is going to be I equals 1 to n, and then we'll take a second sum, j equals 1 to m. And these will represent the two indexes for the two variables. And then that would be f of xi, yj, delta x, delta y. Well, what is this going to be summing up? Well, instead of these representing little rectangles with a width of delta x and a height of the function height, what this is going to represent is little rectangles in the xy plane with a width of delta x and a depth of delta y and a height provided by the function height. In essence, these are going to be little rectangular prisms whose base is a rectangle and whose height is determined by the function height at that point, the z value. Well, as you can see, it's just two nested Riemann sums. So let's reconstruct it from inside out. If we were to add on the ever important limit as m and n go to infinity, then we can first pull out the inner one. And of course, the inner one is dealing with y. So in essence, this is the y integral if we just compare it to the Riemann sum above. So I'll need a limit of integration for that. So that's going to be from c to d, and that's going to be f of xi y dy, and then still times delta x. Now, why is it that this represents f of xi and then y? Well, this is the integral with respect to y, and of course, if I'm just integrating with respect to y, then x is considered a constant. But of course, this is just a slice. We're in essence slicing it down the x-axis so that each function is defined in terms of the x value, and then we're integrating it along the y direction. We still need the summation out front that takes care of the I values. So that's I equals 1 to n, and I still want the limit of this as n approaches infinity. So in essence, I've evaluated the sum over m, and that's turned into an integral in y with respect to y, where x is held constant. Well, you can see we can apply that same criteria a second time, because now this is the summation of this function, and when I complete this integral, there won't be a y left. This will just be a function of x, because I'm integrating with respect to y, and I'm going to plug in two limits in terms of y. So all that will be left of this integral is a function of x, and I'm summing that dx using this integral to find the height as well as the width. And this is going to give me an integral over an area times a height, and of course that's going to be a volume. So let's look at what happens if we apply the rule for the Riemann sum a second time. So that means applying the x portion of it. So now I'm going to end up with an integral from a to b, an integral from c to d of f of x, y. And then now, remember, the c to d, that was the dy portion, so it's dy dx. Now, this looks like a piece of calculus you've never seen before, and at first glance it can feel really intimidating, multiple integration. Notice that there's an inner function that has to be integrated before the outer function. So the order of dx dy is really important. The inner differential also refers to the inner integral symbol and the inner limits. So these are the limits in y. I need to take the integral in y first, and then when I'm done with that, I take the integrand, the completed integral, and that gets plugged into an integral dx. When I'm integrating with respect to y, x is held constant, and when I'm integrating with respect to y, of course, to x, there won't be any y's left, so it will just be an integral of a function that has x's and constants in it. These are definite integrals because we're integrating between limits, so we never have to worry about adding constants. But of course, if these were indefinite, we would add constants for the y portion of the integral and then the x. Now, the geometric interpretation of this is pretty simple. If a Riemann sum added up a series of rectangles that gave me an area, then a double integral of a two-dimensional function is then going to add up a series of rectangular prisms that gives me a volume. This will be the volume of the function f of x, y between it and the xy plane, between the limits of c to d on the y-axis and a to b on the x-axis. In this case, it would be a rectangular base and everything up to and including the function value. Taking double integrals is not difficult. As a matter of fact, it'll utilize the same muscles that you've already developed doing partial differentiation. This, in essence, is the reverse of a partial differential of a function. Instead, you're doing a partial integration, and you'll integrate with respect to the inner followed by the outer. Now, fortunately, the order for those doesn't matter, and you can try that by running through a few examples of your own. If I were to flip the limits of integration and flip the two differentials, I could take the integral with respect to x followed by y, or the integral of y followed by x, and I should get the same answer both times. The same reason that when we do partial differentiation and we get the mixed partials, doesn't matter if you do fxy or fyx, they should be the same, and the same is true here. As long as f of xy is well behaved over the interval where we're integrating it, we should notice there's no difference in the order. Now, as I indicated, the interpretation of this is that it finds the volume. And of course, these are the simplest case scenarios because our limits of integration simply form rectangular bases. What we'll see is that's not always the case. We might want to integrate a function over a base that's not a rectangle. We might actually want the edges to be functions of their own. And we'll cover that in our next presentation.